This is a continuation of our lecture on congruences, and we'll start with the review. So let M be a positive integer, and let A and B be any integers. Z is the set of integers. We write A congruent to B mod M. And how do we read this? Again, A is congruent to B modulo M, or sometimes just mod M, if M divides A minus B. So this is a relation on the integers. That is a subset of Z cross Z. And this relation has some very nice properties. First of all, it is reflexive. A is congruent to A mod M for all A in Z, because M divides 0, which is A minus A. M is equal to, 0. I should write like this. M divides A minus A, which is 0. Okay. 0 is M times 0, so M divides 0. So every integer is congruent mod M to itself. It's symmetric. That means if A is congruent to B mod M, then B is congruent to A mod M. And the proof is very simple. If A is congruent to B mod M, then M divides A minus B. So A minus B is M times some number Q, which implies that B minus A, which is minus A minus B, is minus MQ, or M, times minus Q. So B is congruent to A mod M. And this relation also is transitive. If A is congruent to B mod M, that means A minus B is M times Q for some integer Q. And if B is congruent to C mod M, that implies B minus C is M times Q prime for some integer Q prime. And if we add these equations, the B's cancel. A minus C is MQ plus MQ prime, which is M Q plus Q prime. So A is congruent to C mod M, because A minus C is a multiple of M. M divides A minus C. So we put this all together, and we get that the relation congruent modulo M is an equivalence relation. That is a relation that is reflexive, symmetric, and transitive. And so an equivalence relation on a set partitions the set. So the equivalence classes are called congruence classes. Modulo M. And the congruence class of an integer A is the set of all integers B such that A is related to B. A is congruent to B mod M. Another way of writing this is the set of all integers B such that A minus B is MQ for some quotient, some integer Q, which is the same as saying all integers B such that, let me just rewrite this. This is B equals A minus MQ for some Q and Z, which is all integers B, such that B equals A plus MQ, because Q is positive or negative. So we can write this as, well, that's exactly what it is. I can write it in the following notation, A plus MZ, where MZ is the set of all multiples of Q. So that's 0 plus or minus M plus or minus 2M plus or minus 3M and so forth. So this is what a congruence class modulo M looks like. How many congruence classes are there? What are the different congruence classes? Well, by the division algorithm, every integer A can be written A equals, divide by M, MQ plus R, with the remainder R, which is an integer between 0 and M minus 1. So A is congruent to R mod M. So every integer belongs to one of the congruence classes. Zero plus MZ, 1 plus MZ, 2 plus MZ, up to M minus 1 plus MZ. And of course, 0 plus MZ, we can just write as MZ. So there are at most M different congruence classes. I claim they're exactly M congruence classes, that no two of these congruence classes are the same. So suppose we choose integers R and S between 0 and M minus 1. So if R is congruent to S mod M, then R minus S is some multiple of M. But R and S are between 0 and m minus 1. 0, m minus 1, R, S. The distance S, R minus S in absolute value, it's at most the distance from 0 to m minus 1. If in this equation, Q is equal to or greater than 1 in absolute value, then the absolute value of R minus S is the absolute value of Q times M, which is at least M. But we have a contradiction, because on the one hand, the absolute value is the most m minus 1. If Q is at least 1 in absolute value, the absolute value is greater than or equal to m. That can't be. So therefore, Q must equal 0. It can't be non-zero, which means R equals S, which means there are exactly m congruence classes modulo m. So we have m congruence classes modulo m. Let Z, this is how we write it and how we say it, Z mod mz. Z mod mz be the set of m congruence classes mod m. So Z mod mz consists of m different sets. So for example, suppose m is 2. So Z mod 2z consists of 2 sets, 2z and 1 plus 2z. What are these sets? 2z are the multiples of 2. This is the set of all even integers. What is 1 plus 2z? Well, it's every number which is 1 plus an even integer. 1, 1 plus or minus 2, 1 plus or minus 4, 1 plus or minus 6, and so on. What is this set? I have 1, 3, and minus 1, 5 and minus 3, 7 and minus 5, and so on. I can just rearrange this. This is the set 1, 3, 5, 7, minus 1, minus 3, minus 5. This is the set of odd integers. So Z mod 2z is a collection of 2 sets of integers, the evens and the odds. So that's something you know very well. What about Z mod 3z? This is the set of congruence classes modulo 3. So it consists of 3 congruence classes. The multiples of 3, 1 plus the multiples of 3, 2 plus the multiples of 3. 3z is just 0 plus or minus 3 plus or minus 6 plus or minus 9 and so forth. 1 plus 3z is all the integers that leave a remainder of 1 when you divide by 3. 1, 4, 7, 10, 13, and so forth. And the negative numbers. 1 minus 3, 1 minus 6, 1 minus 8, so forth. This is just a set of all numbers of the form 3q plus 1, where q runs through all the integers. This is what is called sometimes an arithmetic progression. And 2 plus 3z, this is the set of all numbers which, when you divide by 3, leaves a remainder of 2. And this is also an arithmetic progression. Every integer that you can write in the form 3q plus 2, and q is z. I mean, notice that, for example, minus 7 is 3 times minus 3 plus 2. Right? So these numbers, when you divide them by 3, they all leave a remainder of plus 2. Let's look at one last example. What about if you take m equal to 10? Z mod 10z will consist of all numbers, or the congruence class is mod 10. So there are 10 of them. 1, 2, all the way up to 9 plus 10z. What does a congruence class mod 10 look like? Well, what is 7 plus 10z, for example? This is 7 plus a multiple of 10. 0, 17, 27, 37, 8,927. Yeah. Minus 3, minus 10. Why minus 10? Oops. Yeah, why minus, sorry. Why minus, I shouldn't say minus 10. Minus 13, minus 23, and so on. Why minus 23? Minus 23 is 7 plus 10 times minus 3. 7 minus 30 is minus 23. In general, for any digit r, from 0 up to 9, r plus 10z consists of all the positive integers with the smallest digit equal to r. I should actually say the non-negative integers, in case r was 0. Together with all the negative integers with smallest digit 10 minus r, if r is non-zero, or 0 if r equals 0. So the congruence classes mod 10 are completely determined by the unit digit, the smallest digit in the decimal expansion. Now, just the way we can add and multiply integers, we can also add and multiply congruence classes. So I want to define addition of congruence classes. And the way we want to define it is as follows. If I take the congruence class A plus mz and the congruence class B plus mz, I want that to be the congruence class of A plus B plus mz. And we need to show this is well defined. And what do I mean by that? Well, for example, suppose I take m equal to 7. So we know the congruence class of 5 plus 7z is the same as the congruence class of 19 plus 7z, because 5 minus 19 is minus 14, is 7 times minus 2. And the congruence class of minus 4 plus 7z is the same as the congruence class of 24 plus 7z, because minus 4 minus 24 is minus 28, is 7 times minus 4. So in order for addition to make sense, it has to be the case that 5 plus 7z plus minus 4 plus 7z is the same as 19 plus 7z plus 24 plus 7z. Well, the way we define congruence, this is 1. Let me just write it. This is 5 minus 4 plus 7z. 5 minus 4 is 1 plus 7z. And the way we define congruence classes, this is 19 plus 24 plus 7z. 19 plus 24 is 43 plus 7z. Are these equal? Well, 1 plus 7z is equals, or let me wait this way. 43 is congruent to 1 mod 7, because 43 minus 1 is 42, is 7 times 6. So 1 plus 7z equals 43 plus 7z. So if we wanted to add these two congruence classes, we can write a congruence class in infinitely many different ways. 5 plus 7z equals 9 plus 7z, and minus 4 plus 7z equals 24 plus 7z. So if I define the addition of this congruence class by taking these representatives, or by these representatives, we still get the same congruence class. So this is just an example. Maybe we were lucky this time, but no, we weren't just lucky. This is always true. So I'm going to prove that addition of congruence classes is indeed well defined. So this is the proof that addition of congruence classes is well defined. So suppose A is congruent to A prime mod M, and B is congruent to B prime mod M. So A minus A prime is M times some number Q. And B minus B prime is M times some number T. So A equals A prime plus MQ. B equals B prime plus MT. If I add, A plus B equals A prime plus B prime plus m times q plus t. So a plus b is congruent to a prime plus b prime mod m. So the congruence class of a plus b mod mz equals the congruence class of a prime plus b prime plus mz. So whether I take, so this means that if I take a plus mz and b plus mz, if I add those congruence classes, I get a plus b plus mz, which is a prime plus b prime plus mz, which is a prime plus mz plus b prime plus mz. End of proof. Addition of congruence classes really is well defined. I want to define multiplication. Of congruence classes. And again, suppose A is congruent to A prime mod M. So A equals A prime plus MQ for some Q. And suppose B is congruent to B prime mod M. So B equals B prime plus MT for some T. What is A times B? A times B is A prime plus MQ times B prime plus MT. If I multiply out, I get A prime B prime plus M A prime T plus M B prime Q plus M squared QT. This is A prime B prime plus M times the integer A prime T plus B prime Q plus M QT. So AB is congruent to A prime B prime mod M. So if I want to define multiplication of congruence classes, so let A plus MZ times B plus MZ, this is the definition. This has to be a congruence class. As AB plus MZ. And this is well defined because if I choose the congruence class A prime plus MZ and the congruence class B prime plus MZ, I get A prime B prime, but A prime B prime is congruent to AB. So this is well defined because, let me just check that it's well defined. I'm really just repeating the same argument. If A plus MZ equals A prime plus MZ and B plus MZ equals B prime plus MZ, then A plus MZ, B plus MZ, that's AB plus MZ, but AB is congruent to A prime B prime. This is A prime B prime plus MZ. So this is A prime plus MZ times B prime plus MZ. So we have a consistent way to multiply congruences and to multiply congruence classes. Now, addition of integers and addition of congruence classes share certain properties. So let me make a little table. Addition of integers, or I should say addition in the set of integers. And I want to list also properties of addition in the set of congruence classes mod z. So the first property that both of these addition operations have is associativity. If you take integers a, b, and c, a plus b plus c equals a plus b plus c. We say that the operation of addition of integers is associative. What about addition of congruence classes? If you take a plus mz plus b plus mz and you add them together, and then add the congruence class z plus mc to that, what do we get? This is the congruence class a plus b plus mz, and we're adding to it the congruence class c plus mz. This is the congruence class a plus b plus c, this integer, plus mz. But because addition of integers is associative, this is the same as a plus the integer b plus c plus mz, because these two numbers are the same. And if you unwrap this, you get a plus mz plus b plus c plus mz, which is a plus mz plus the sum of the congruence classes b plus mz plus c plus c plus mz. And this is the associative law for addition of congruence classes. So addition of the integers is associative, so is addition of congruence classes. In the integers, we have an identity. 0. 0 plus a equals a plus 0 equals a for all integers a. In the congruence classes, for any congruence class a plus mz, mz plus a plus mz, which is the same as 0 plus a times mz, is a plus mz, which is a plus 0 plus mz, which is a plus mz plus mz. So in this finite set of congruence classes, the congruence class mz is the additive identity, just the way the integer 0 is the additive identity. In the integers, every integer has an inverse. So for any number a, there exists a number minus a, such that a plus minus a and minus a plus a is 0. And for congruence classes, for any congruence class A plus mz, there's also the congruence class minus A plus mz. And the sum of these is A minus A plus mz. This is just 0, that's mz. And similarly, minus A plus mz plus A plus mz equals 0 plus mz, or mz. So every congruence class, mod m, has an inverse. And the last property I'm going to note about addition of integers and congruence classes is what we call commutativity. A plus B and B plus A are always the same. It doesn't matter what order you add in. And if I take A plus mz plus B plus mz, that's the congruence class A plus B plus mz. But the integer A plus B is the same as the integer B plus A. And this is B plus mz plus A plus mz. So addition of integers and addition of congruence classes share these four properties. Addition is associative, there's an additive identity. For every element, there's an inverse, and addition is commutative. So these are fundamental properties that you find in many different places in mathematics, and they both lead us to the definition of a group. So in the case of the integers and the congruence classes, we've talked about addition. We also talked about multiplication. Addition and multiplication in Z and in Z plus MZ are examples of binary operations on a set. A binary operation is simply a way to assign some element to every pair of elements in the set. So we could say, if we wanted a very formal definition, a binary operation on a set, I'll call it X, is a function from the set of ordered pairs of X to X. I mean, just like a function of two variables. F of X, Y is some number Z. So for example, for addition, F of X, Y would be X plus Y. For multiplication, well, G of X, Y would be X times Y. So these are examples of binary operations. Given any two elements in the set, you assign a third element to it. Of course, you saw this in Calc 3 whenever you have a function of two variables, a real valued function of two variables. When you graph it in three-dimensional space, you just get some surface. Those are generally much more complicated operations than what we're considering, but addition and multiplication are what we're considering. And whenever you have a binary operation on a set, you can check, is it associative? Is there an identity element? Does every element have an inverse? And is it commutative? And a binary operation on a set that satisfies these properties is called a commutative group or an abelian group. So let me just write down the very fundamental definition of a group. So a set G with a binary operation could be written as addition or multiplication or anything else, is a group if the operation is associative, an inverse exists, as an inverse, and if has an identity, and every element has an inverse. So if we wanted to write down what this means, then we write it in both addition and multiplication. Associativity means A plus B plus C is A plus B plus C. And under multiplication, it means A times B times C is A times BC. And identity means, well, that's right, the additive identity is 0. There exists a 0, an element in the set, where A plus 0 and 0 plus A equals A. We often write the multiplicative identity as 1. 1 times A and A times 1 equals A. And to say that the element has an inverse, for all A, there exists a B such that for an additive group, A plus B and B plus A equals 0. And for a multiplicative group, A times B and B times A equals 1. And we often write B as minus A if the operation is addition, and B is A to the minus 1 if the operation is multiplication. So a group satisfies these three properties. A commutative group, or also called an abelian group, is a group that also satisfies the commutative rule. It's a group that is commutative. So under addition, A plus B equals B plus A. And under multiplication, we would write A times B equals B times A. So this is the definition of a group and an abelian group. And we've seen two examples. The integers under addition and the congruence classes under addition. What's an example of a multiplicative abelian group? Well, we could take, I'll write Q star, this means the non-zero rational numbers, fractions, is a multiplicative abelian group. What's another example? Suppose I take the group, I'll use this funny notation, SL2Z. By this I mean the set of all 2 by 2 matrices where A, B, C, and D are integers, and the determinant AD minus BC equals 1. So you should know about 2 by 2 matrices, either from wherever or from linear algebra. And multiplication of matrices is associative. The matrix I equal 1, 0, 0, 1 is the identity. And if A, B, C, D, I'll call this X, is an SL2Z, suppose we let Y be the matrix D minus B minus CA. Now, if I check the determinant, I'll see this is an SL2Z. This is an SL2Z because DA minus B times minus C is AD minus BC is 1. So if this is an SL2Z, so is this. And what is X times Y? X times Y, A, B, C, D, D minus B minus CA. If I multiply, I get AD minus BC minus AB plus AB, CD minus CD, minus BC plus AD. This is 1, 0, 0, 1. That's the identity. So Y is an inverse on the right. What about Y times X? This is AD, oh, sorry, Y, that's the Y. Forgot to write down the X. A, B, C, D. This is AD minus BC, BD minus BD, minus AC plus AC, AD minus BC. This is also 1, 0, 0, 1 of the identity. So Y is the inverse of X. So SL2Z is a group. Let me try and squeeze in an example. Suppose I take the matrix, I'll just give it a name, R. Maybe this is the matrix 3, 2, 4, 3, and S is the matrix 1, 5, 1, 6. So each of these has determinant 1. Let me multiply them together. RS is 3, 2, 4, 3, 1, 5, 1, 6. This is 3 plus 2 is 5. 15 plus 12 is 17. 4 plus 3 is 7. 20 plus 18 is 38. And if I take S times R, 1, 5, 1, 6, 3, 2, 4, 3, this is 3 plus 20, 2 plus 15, 3 plus 24, 2 plus 18, These aren't even close. So RS is not the same as SR. So SL2Z is a non-abelian group. So most of the groups we'll see in the beginning are abelian, but it's important to know that there are many non-abelian groups, and you should know about matrix multiplication. And matrix multiplication shows us that the set of 2 by 2 matrices with integer coordinates A, B, C, D, and determinant equal to 1, this is a multiplicative group. The identity matrix is the group identity, but it's not abelian. That's a very important group.